Hi there, welcome back to this channel. In this video, we are going to be discussing static electricity, but this time we are not just going to be, we have dealt with the introduction in the first video, so I will link that video in the description. Today we are going to be solving calculations, and I am going to implore you to stick with me till the end of this video, because I'm going to be unveiling some tips to us to be able to use in exams. And of course, as a bonus tip, I'm going to be solving a lot, some JAMB questions. And over time, I have studied that the concept of capacitance and all are one of the most most asked part of this electrostatics. But of course, they also ask electric field, electric force, and all of that. So we are going to really do justice to those ones, and of course, discuss the concept of capacitor. But if you think you already know the force and electric field aspect, you can always skip to close to the end of this video. We'll be talking about capacitor and capacitance. But just make sure it will do you more good to watch the video from beginning to the end, because it's going to, be chronologically linked to each other. Is that okay? All right, and we are going to be using the JAMB remix series, to take past questions. All right, so we have the first thing we want to discuss is the electric force. Electric force. Now you remember, if you have seen that video that I released the last time, I have talked much about the introduction of this electric force. In that video, we talked about the fact that if we have two charges, according to Benjamin Franklin, there are two types of charges. There are the positive charge and the negative charge. So we have those two charges in a point. They exert a force upon one another. If they are unlike charges, the force will be attractive. Of course, for them to move close to each other, there is an impetus, and that impetus is force, all right? So that force has a magnitude. Is that okay? So according to Charles Auguste de Coulomb, Charles Auguste de Coulomb. How do you spell it? Coulomb. All right, I think it's like this. Coulomb. That was in 1770 something or thereabout. Charles Auguste Coulomb, after much experiment, was able to come up with the proposition that we now call we call it Coulomb's law of electrostatics, Coulomb's law of electric charges. And that force is said, the force of attraction or repulsion, the force F. And for WAEC students, if we're stating laws, this is how you are going to be stating it. Is that okay? All right, but of course, in JAMB we don't state that, so just watch me. The force F of attraction, if attraction, what does that mean? Unlike charges. Or of repulsion, like charges. Between two charges is directly proportional to the product of the charges. So let's say the charges are Q, capital Q, and small q. All right, so the force of attraction between them, or repulsion between them, is equal to the product of the charges, but that same force is inversely proportional to the square of the distance between them. So you are going to see d squared or r squared, depending on the convention you are used to or your textbook. I'm going to stick with the r squared convention for distance. So I restate that. It said the force of attraction or repulsion is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. Now, mathematically, that would become F is equal to, by the time we introduce equal to, there's got to be a constant of proportionality, and the constant stays here. Then we have Q and Q over R squared, owing to the fact that this is a joint variation. All right, so the force is directly proportional to the product of the charges or inversely proportional to the square of the distance between them. What that means is this. Now, if you have seen the video I released on, I'm going to link that also in the description, on how charges relate, on how formulas relate. You will understand what I want to say, that the higher, because this F and this QQ, two Q's are on the same level, they are numerators. It means that they are directly proportional to each other. I mean, according to the law, it says that also. Now, it means that, the implication of that is that as the charges increase in magnitude, or as the magnitude or sizes of the charges increase, say for example, it goes from 3 microcoulomb to 1 microcoulomb, or to 2 millicoulomb, as it's increasing like that, the force, the magnitude of the force will also be increasing in like manner. All right, so this is what we have, therefore. Also, the R, which stands for the distance between them. R is the distance between them. Q1 and Q2 are the two charges, or QQ. I'm putting them as QQ here because they are different, they might be different charges. Now, the force of attraction repulsion between them is directly proportional to the square of the distance between them. Here, if what this tells us is that here, the larger the distance between them, the less the force of attraction or repulsion they will feel. And see it is squared. It is squared. It means that only a little change in the distance between those charges. Say I put charge 1 here. Let's say it was a point positive charge, and I put charge 2 here, and it was a point negative charge. Now the force of attraction between them is going to be inversely proportional to the square of the distance between them. The distance between them matters. All right. So the distance between them matters. Now, it means that because of this square here, it means that the distance between them has a very huge role to play. That is, a little change in the difference will lead to a little change in the distance, rather, will lead to a great change in the force. Is that okay? And of course, if it's increasing for the distance, it will be reducing the force. And if it is reducing the distance, if the distance is reducing, the force, of course, will be increasing because of inverse proportionality. All right, that said, of course, now this line I'm drawing here, the law completely says that this is directly proportional to the charges, pair of charges, but inversely proportional to the square of the distance between them. In line and acts, that force acts in line of the in direction of the line joining them. The force acts in direction of the line that joins the two forces, so two charges. So these two charges here, they'll be joined, they're joined by joined by this line. So it means that the force of attraction is along this line. All right. Now let's talk about, let's put that into working. Let's see what that is. Okay, we have not even talked about the constant of proportionality. Now let me talk about the constant of proportionality. Now, you see this K, our K here, is another constant that stands for 1 over 4 pi epsilon naught, according to Coulomb. So an epsilon naught here represents permittivity of free space. Permittivity of free space. Now, we know the value of pi. The value of epsilon naught is equal to 8.85 times 10 raised to the power minus 12. Times 10 raised to the power minus 12. Now, it has its own unit, so I'm going to derive the unit for us. The unit of force, of course, is Newton. I'm going to derive the unit of this guy also. The unit of the constant here, but let's derive the magnitude first. Now you're going to have that if this is the value there, then we have that K is equal to 1 over 4 times 3.142 times 8.85 times 10 to the power minus 12. That is 1 all over all of this. By the time you plug all of this into your calculator, you are going to come out with approximately, you're going to come out with about 8.9, which is approximately 9 times, so K, the value of K is equal to 9 times 10 to the power 9 Newton. Now it is Newton meters squared per Coulomb squared. And how did I come up with that? From here, we know that F, recall that F is QQ over R squared. I've told us before that the unit of Q, the unit of charge is Coulomb, of course. So K will therefore be equal to, by now, cross multiply, we have KQQ equal to FR squared. Alright, then K will therefore be equal to FR squared over QQ. And F is Newton. R is meters squared because it's squared. R is distance. This unit of distance is meter over Coulomb. That is what? Newton meters squared over Coulomb squared. So that is what we have there. Per Coulomb squared. Per means over. All right. So now let's put that into work. Let's see if we can resolve a question with that law. The law of Coulomb. Okay. Now this guy said has its own unit also. So it's going to be the inverse. It's going to be the inverse of these guys because these are constants. So it's going to be the inverse of this guy. All right. And what does that mean? The inverse of this guy will just what? Will be C squared per Newton meter squared. That will be the unit of what? Permittivity of first place. That is just for the record. Now let's solve a particular question now. Now, if a question says that find the force of attraction, the force, it could be asked, is the force going to be attractive or repulsive? All you have to do there is check the signs on the charges. If it's the same sign, they will repel. If it's different signs, they will attract. So find the force of attraction between 3 microcoulomb charges that are placed at a distance 9 centimeters between each other. Now with this, you'll be given the constant of proportionality and all of that accompanying your question. All right, so how do you solve this kind of question? Find the force, not force the force. Find the force of attraction between two. So this is how you go about solving it. You recall, let's write solution. You recall that the force F of attraction, this case attraction because there will be one will be positive, the other will be negative. Okay, but in this case, it is the same charge. So let's turn it to repulsive. The force of repulsion. All right, so repulsion between those guys because it's similar charges. So F will be equal to KQ over R squared. Now, what is our first Q? Since the charges are equal, we have QQ to be 3 microcoulomb. Now, take note of this word, this sign, mu. Mu is a Greek alphabet. And in mathematics or science, we use it to represent micro. We represent micro, and it stands for times 10 to the power minus 6. If we come down, we're going to have milli. So that's why we have millimeter. Milli means times 10 to the power minus 3. All right. Now, if you see new Coulomb, it means that thing times 10 to the power minus 6. Now, another one is if you go down again, we're going to have nano. Nano is less. Nano something means, I said nano, means times 10 raised to power minus 9. Down again, you're going to have another one, which is pico. And we continue like that. We have zeta and all. So pico is going to be times 10 raised to power minus 12, whether pico or pico, whatever that is. Now, for the purpose of this your JAMB, you will not see anything beyond this. Is that okay? So we have this, our charges. So this guy means 3 times 10 raised to power, it's a microcoulomb, minus 6 coulomb. This is micro. Is that okay? So this one will also be equal to 3 times 10 raised to power minus 6 coulomb. All right, now, how do we employ? Now, I said they are placed at a distance 9 centimeters between each other. Recall that the unit of distance is meter. So here, the distance r will be equal to 9 centimeters, which will be equal to 0.09 meters. 0.09 meters, right? So what we are going to have will be F will be equal to K. What is our K? Recall that K is what? 9 times 10 raised to the power 9. Then times our Q1, 3 times 10 raised to the power minus 6. Q2, 3 times 10 raised to the power minus 6. Is that okay? All over R squared. What is our R? R is 0.09. Then all of this squared. And what does this give us? We have that F will be equal to 9 by 3 by 3. That is 81. 81. So we have 81 times 10 raised to the power 9. Multiplication of the bases will result in addition of power. So that will be 9 plus minus 6. Plus minus 6 is minus 6. Plus minus 6 again. That is minus 6. All over 0.09. This means 9 times 10 raised to the power minus 2. So if I square this, it will be this squared, 81 times 10 raised to the power minus 4. Does that make sense? So we have 81 times 10 raised to the power minus 4. So at here, we just cut this and we have 1. Is that okay? Times 10 raised to the power 9 minus 6 is minus 12. Here, division means minus, then minus 4. Does that make sense to you? This becomes 1 times 10 raised to the power 9 minus 12 plus 4. Does that make sense? So from here we have 1 times 9 raised to the power 9 minus 12 is minus 3. Minus 3 plus 4 is 1. Okay, so 9 minus 12 is what? Minus 3. Minus 3 plus 4, that is just 4 minus 3. That is 1. So the answer is 10 Newtons. Right, and that is the force of attraction between two charges. Good. Now let's go to the next one, which is the electric field. Let's talk about the electric field. Let me pause. Now, let us talk about the electric field. Now, the electric field, we said in the previous video, there's a region in space around a point charge where the magnitude of the force due to that charge is felt. So who will feel it? A test charge. The charge that is having an electric field around it is the source charge. So there are two charges. There is the source charge. The source charge means the source of that electric field. Every point charges has what? An electric field surrounding it. We discussed this before. Now, if you look at it here, we said that it's represented with electric field lines, right? And if you look at the lines well, we said it's represented with electric field lines. If you look at the lines here, you see that they are kind of divergent, right? They are divergent. It means that as you go away from the charges, what you feel, the amount of force that you feel due to this charge begins to reduce. The amount of force that you feel due to this charge reduces. So we are seeing that it's going radially outward from a point positive charge, or a source positive charge. But it will go radially inward for a point negative charge. Now see this. The closer you are to the electric field of into the electric field, the stronger the force you feel. I have explained this in detail in the previous video. But my point is this. This charge here will be called the source charge, the one producing the electric field. Now, to now measure the electric field on a particular charge at a particular location, we will use what is called a test charge. Now, the formula involving test charge and source charges are different. They are not exactly different, but they refer to them in different ways. So, for example, now another way to define electric field is the force felt per unit of charge placed in the field of this charge. So if I at a particular point for this charge, if I put a unit positive charge somewhere around this field here, for example, given the distance between them, is that okay? If I have a unit charge, if this was 1 Coulomb, then it means that the force on this test charge, this will be called my test charge, of course, the force on this test charge will be equal to the force that exists at this region around the charge. the force that will be felt by this 1 coulomb is the force around that region due to this charge. But the force, but the electric field that will be felt by this guy, I will call that electric field strength or electric field intensity. Electric field intensity. Now that is, electric field intensity is a scalar quantity, but electric field is a vector. Is that okay? Now we said electric field intensity or electric field strength. Now, the strength felt by a point charge here, by a point positive charge here, is going to be the force per unit of this charge placed at that point. Okay? Now, we said that electric field intensity or electric field strength will be equal to what? The force felt per unit of charge placed at a particular point. The force felt per unit of charge. So let me give us the two equations. So it's either you use this or recall first that our F is equal to KQQ over I squared, right? So from here, we can substitute this guy into the equation. And we have the electric field strength is equal to F, which is KQQ. Next time, just bring this guy down. R squared times what we have here is Q. Is big Q. Does that make sense to you? So what we have here is big Q. So this place you have here is force. Is that okay? Now, Q will take care of Q. Then our electric field intensity becomes KQ over R squared. Now look at this. With this Q here, this is where I was trying to refer to, or what I was trying to refer to. Q here is the source charge. The source charge. That is the charge that produces the electric field. That is it. Its magnitude. Then on this place, Q here is the test charge. The big Q here is the what? Is the test charge. Alright. Now, so we said that depending on the points, the electric field intensity may increase or decrease. Now look at this. The electric field intensity at this point cannot be compared to the electric field intensity at this point. And why is that? It is because the closer you are to the force that has that electric field, the stronger the force that you feel. If you are positive, the stronger the repulsive force you feel. If you are negative positive, the less the repulsive force will be. Right. So that is electric field intensity. Now, what if we wanted to talk about the electric field intensity at different, due to different charges, due to multiple charges? So let's write that. We said electric field intensity due to multiple charges. All right. Now, the electric field intensity due to multiple charges simply says that if I have, simply means rather that if there are two charges, for example, the multiple charges means more than one charge. Is that okay? If there are two charges, the one is positive, the other is negative. Now, what do you expect between them? They have to attract, right? But what will be the intensity of the electric field intensity of these two charges upon each other? Or at a point, the magnitude of the electric field at a particular point, let's say P. So this guy is at his field towards the direction, and like that. Then here, this guy's field is also coming like this, but this time it's going inward, right? So because of that, these guys, this point, the point P, will have a strong field on the electric field. All right, now let's solve a question involving electric field intensity and electric field. Let me pause. So this question says, We should calculate the electric field intensity due to a 5 microcoulomb charge at a point P, 6 centimeters away in its field. So there is a point P. Once you see that you are talking about the source charge, remember, this is the formula you use. So E is what we're looking for. We don't know. Now we know K, 9 times 10 to the power 9 Newton meter squared per Coulomb squared. Now, Q, which will be our source charge, is 5 microcoulomb. That is 5 times 10 to the power minus 6 coulomb. Then R, the distance, is what? 6 centimeters, which is 0.06 meters. So with this, we can now calculate using the formula. E is equal to KQ over R squared. This will become K, which is 9 times 10 to the power 9 times Q, which is 5 times 10 to the power minus 6, all over R, which is 0.06 squared. It's going to give us 9 times 5, or let's just make it 9 times 5, let's just separate it for the 5, I thought I was separate it before, times 10 to the power 9 minus 6. Is that clear? So from here, over 36 times 10 to the power minus 4. 36 times 10 to the power, yes, minus 4. Right. So from here, we can now go on to saying that 9 here, 4, 9 here, 5. Alright. So this will now become 5 over 4 times 10 to the power 9 minus 6, 3. 3 minus 4, that's 3 plus 4. That is times 10 to the power 10. And 10 to the power 7 Newton per meter. Newton. Now what's the unit of electric field? Remember that it is F per Q, that will be Newton per Coulomb. So that's the SI unit. I mean, let's convert this to decimal fraction. That will be 1.25 times 10 to the power 7 Newton per Coulomb. Alright, so that will be the magnitude of electric field intensity at that point at the 6 centimeter away. But, so what that means is that if I place a point charge that is 6 centimeters away from the magnetic field, the electric field of that charge, you take it that far, the intensity will be very, very low. Okay. Right. Now, let's go to, what if we had multiple charges? So now tighten your seatbelt because I'm going to solve a long question. All right, so let's solve these questions. It says 3-point charges of magnitude minus 4 microcoulomb, minus 5 microcoulomb, 3 microcoulomb are arranged in the following way. So they are arranged this way. So the distance between this 4 and a point P. So all of them are exerting their electric force or their electric field extends to a point P. So, but there are 3 charges, and we want to know the magnitude of the electric field intensity that will be felt at this point. He said calculate the electric field intensity at point P. So this guy has electric field intensity extends towards point B, and of course abroad, extends towards point B, of course, to other parts, and minus 5 extends towards point P in this direction, and of course to every other part of the surrounding. So, but we want to know the electric field intensity that a 1 Coulomb charge, if placed at this point, we feel. That is what we want to examine. All right. And of course, the force on a 2 microcoulomb is placed at that point. So we want to know what that is. Now let's calculate the first one. Now follow me because the first one is it looks tricky. I mean, some students consider it uneasy to do, so just watch me. The first one says calculate the electric field intensity at point P. In order to know the electric field intensity at point P, there are 3 charges here that are acting at point P. So we have to know the intensity due to this guy, the intensity due to this guy, and the intensity of that guy. Is that okay? At this distance. Do you understand? The intensity of this guy at this distance. So if you are standing at this distance, away from this guy, what is the force that you feel at this point? At this point, away from this guy, what's the force you feel? At this point, away from this guy, what's the force you feel? That's what we need there. If you are a unit Coulomb. All right, now it says the electric field intensity at that point. So let's get the electric field intensity for the individual charges. So the E1, let's call this one E1. Let's call this E1. Let's make this our E2 and this E3. Now E1, remember, is force per unit charge, right? Which is equal to KQ over R squared. We derive that in the former equation. So this will become K, which is always 9 times 10 to the power 9 times the charge. Now E1 is what? Minus 4 microcoulomb. Now that minus is not really going to affect our calculation of the electric field intensity at all. I'm going to tell you what that minus will tell us to do here. Now, so we have 9 times 10 to the power minus 9, so times the charge is 4 times 10 to the power minus 6 because it's micro. Over the distance away from that point P is 6 centimeters. So R is 6 centimeters, which will be 0.06 meters. So that will be 0.06 all squared. So this becomes 9 times 4, that is 36, times 9 raised to power, times 10 raised to power 9 minus 6. All over this will invariably turn to 36. When you have something like this, just square this guy, and then write times 10 raised to power minus 4. Especially when it's given as a unit centimeter. The unit place numbered centimeters. So we have this guy. Okay, so 36 takes care of 36, and then we have 10 raised to power 9 minus 6 is 3 over 10 raised to power minus 4. This becomes 10 raised to power 3 minus 4. That is 10 raised to power, division, this thing. And for those of you that don't understand what I did here, this becomes 10 raised to power 3 divided by 10 raised to power minus 4. So recall in indices that we have 8 raised to power m divided by a raised to power n. It's becoming a raised to power m minus n, isn't it? So this becomes 10 raised to power 3 as a multiplication of the division of the basis, subtraction of powers. So we have subtraction of these powers. Is that okay? This becomes 10 raised to power 7, that is minus times minus plus, or minus minus plus, that is 10 raised to power 3 plus 4, which is 7. Now, Newton per Coulomb, or you say 1 times 10 raised to power 7 Newton per Coulomb. So E1, let's write E1 somewhere here. So E1, we got to be what? 10 raised to power 7 Newton per Coulomb. Now let's go. Let's calculate for E2. Is that okay? Now let's calculate for E2. Now for E2, our Q2 this time is 3 microcoulomb. Is there minus? There's no minus. So E2 will become KQ2 over R squared, right? The electric field intensity due to that Q2. So this becomes 9 times 10 to the power 9 always, times 3 by 10 to the power minus 6 again, all over. What's the distance from point P? The distance of this charge from point P is 3 centimeters. So 3 centimeters, R is 3 centimeters. So that becomes 0.03 meters. So that becomes 0.03 meters all squared. So this will now give us 9 times 3 is 27 times 10 to the power 9 minus 6 all over. Now if you square this, I said you square this guy to give us 9 times then 10 to the power minus 4. Is that okay? Because this will be raised to power minus 2 times 2, that's 4. So 9 here 1, 9 here 3. So what we have is 3 times 10 to the power 9 minus 6 is 3. Now divided also by 10 to the power minus 4. So this becomes 3 times 10 to the power what? 7. From what we did, that would be 3 minus 4, that would be 7. So Newton per Coulomb. This is E2. So E2, we got it to be 3 times 10 to the power 7 Newton per Coulomb. Now let's solve for E3. Now what will E3 give us? E3, we have Q3. What is Q3? Q3 is given to be minus 5 microcoulomb. What's the distance from that point P? Its distance is 2 centimeters. So that is 2 centimeters, which is equal to 0.02 meters. So as we have this formula, 9 times 10 to the power 9 times, what is this? The charge, 5 times 10 to the power minus 6. Remember, I told you this minus will not affect it yet. Is when we want to determine, because there are 3 charges here, it means that what we need to calculate is the resultant electric field intensity that we need to calculate there. So it is that time that this minus has a role to play in our equation. So what do we have here? The distance apart is 0.02 all squared. This becomes 9 times 5, which is 45, times 10 to the power 9 minus 6 as usual, over 4 times 10 to the power minus 4. 4 times 10 to the power minus 4. So 2 will go here, 2 will go here, 22.5. 2 here, 1. Now 2 here, 11.25. Alright, so what we have is 11.25 times 10 to the power, here will give us 3 still, minus 4. That is plus 4, right? That will now be 11.25 times 10 to the power 7. Now, is that usually you answer like this, or you convert to standard form? But because we are still solving for that, I want to leave my answer like this, so that everything will look like this. Everything will have times 10 to the power 7. With that, I can work with the number easily, Newton per Coulomb. Now, these are my electric field intensities. Now, what is now the electric field intensity at point P? Because there are 3 electric field intensities that are being felt at point P. So what will be the resultant electric field intensity felt at point P? Now, this is the way you calculate that. Now, the resultant first, remember that the resultant, so let's call that electric field intensity resultant, will be equal to the sum of electric field intensities, the sum of E at y-axis, all squared, plus the sum of E's at x-axis, all squared. Do you understand what this is? Exactly, resultant forces. So in this case, we want to calculate the resultant of the electric field intensity at that point P. So what is the sum of electric field intensity in the y-axis? The electric field intensity in y-axis. Which one is acting in y-axis to that point P? Only the 4 microcoulomb. 4 microcoulomb is our E1. Now, this is what you now do. This is where the minus, the charge is now very important to take note of. Now, because the charge is minus, how does the charge act? Now, how does it act? For minus charge, we know that for a negative charge, electric field intensity goes out radially inwards. Inwards, that is in direction of the charge. While for a point positive charge, it will be radially outward, away from the charge. So if this is the case, therefore, then it means that you will understand what I want to do here now. That because this charge is negative, then the field will be felt towards the negative charge. Does that make sense? The field will be towards the negative charge, and the direction of the field here, because it's positive, will be away from the positive charge towards the point P. And here it will be away again towards the negative charge. From point P towards the negative charge. Does that make sense? So what we have here, because the E is felt in the positive Y direction in your Cartesian, you have Y and minus Y, minus X and X. So because the E is felt towards the positive Y, then our EY is going to be positive. So our 1 times 10 raised to the power 7 Newton per Coulomb is positive. So that's our sum of forces, sum of the electric field acting in X in Y axis. How about sum of E field acting in X axis? For the X axis, guys, we have this guy, the 3 microcoulomb is acting in this direction. Now, what direction is this? Is this positive or negative? If you look at the Cartesian, this is what? Positive. If it was negative, you add negative. For example, if this one was negative now, this arrow will point inward, and it will mean that this guy, which is E2, will be minus 3 times 10 to the power 7. But in this case, it is positive. So it is acting away, and away from it is in direction of positive y-axis. So if away from it is in direction of positive y-axis, then this will be positive, then plus. Now this minus 5 microcoulomb is just going to also be into that charge, because it's minus is always inward to the charge. So it's going inward to the charge, and that direction is positive y, this according to your Cartesian. Then what we have, the Cartesian geometry, that's what I'm talking about now. And then because of that, we have that E3 will also be what? Positive. That is 11.25 times 10 to the power 7. So this is it. So we now add this up. 3 plus 11.25, that will be 14.25 times 10 to the power 7. You see why I did not, change this guy now to standard form, because it will be more difficult to work with times 10 to the power 7 and times 10 to the power 8 here. So we have this. All right, then we can now say that our E, resultant E at that point will be equal to the square root of E at y-axis, that will be 1 times 10 to the power 7 all raised to the power 2, that's squared, plus E at x-axis, 14.25 times 10 to the power 7 all squared. So E resultant will now be equal to the square root of 1 times this is this squared will be 10 to the power 14. Is that okay? Plus 14.25 squared. Let's use our calculator for that. 14.25 squared. Okay, times 14.25. That gives us 203.0625. Then times 10 to the power 14. All right. So what we therefore have from here is that now one thing you could do here is this. After squaring this, then we can say that this guy is 1. This guy was 1 times this. Is that okay? So we can collect like terms and say that E resultant will be equal to the fact that this guy 1 times 10 raised to the power this and this times 10 raised to the power this. So 10 raised to the power 14 is common between 1 and 203 point. Let's make this 0.6. Leave it at 0.6. Is that okay? So this becomes E sub r will be equal to square root of 10 raised to the power 14 times 203 plus 1. That will be 204.06. So we can separate this into 2 brackets. Let's bring that here. That will become square root of 14 times square root of 10 raised to the power 14 times square root of 204.06. Or let's just take the square root of that. Square root of answer. That becomes 14.25. Oh, of course, 14.25. So, like, we needed not to square it, because this is okay. So what we have is this will become 10 to the power 7 times 14.25. Right, so our E sub r will be equal to 1.425. I'm converting this to standard form. This will be times 10 to the power 1 times this will now be plus 7. 1 plus 7 rather. That will now be what? Times 10 to the power 8. Is that okay? I'm bringing this, I'm converting it to standard form. And so the answer will be Newton per Coulomb. So this is the electric field intensity that will be felt at point P. The electric field intensity that will be felt at point P. Now, how about the force? Second question now says the force on a 2 microcoulomb charge placed at that point P. So recall that the electric field intensity is the force per unit of charge. We already know the intensity at that point. What is the intensity at that point? It was 1.425 times 10 to the power 8 Newton per Coulomb. That was what we calculated. Then, so what will be the force that will be felt by a charge 2 times 10 to the power minus 6? And that is easy. So what do we do? Since we have this, then it means that F from here will be equal to E times Q. Does that make sense? So our F will be equal to E, which is 1.425 times 10 to the power 8 times 2 times 10 to the power minus 6. So 2 times this will give us F will be equal to 2.85 times 10 raised to power 8 minus 6. That is 2. That will be the answer, newtons. All right. So that is how to find the electric field intensity due to multiple charges. Now I'm going to drop, I'm going to write a question on the board. Now you're going to do this. What if I change this arrangement to something like this? To something like this. So let's put this minus 4 microcoulomb. Let's put it around here. Minus 4 microcoulomb. And the distance between here and here is, let's say, to 4 microcoulomb. 4 microcoulomb. The same question now. 6 centimeters. Here. Okay, let's make this 3 centimeters now. Let's make this like 6 centimeters. Then what is the magnitude of P of electric intensity at the point P here? So what you have to do is just connect them in squares. Now, if you have really understood what I explained here, then try this and give me your answer in the description below for questions 1 and question 2. In the meantime, we are going to go into the next thing, which is electric field potential. Let me pause the video again. Now, let's discuss the next concept, electric potential. Now, what is electric potential? Now, electric potential is the work done in bringing a unit positive charge, a unit point charge rather, whether positive or negative, a unit positive charge from infinity to a particular point, or a unit charge, not a unit positive charge. The work done that you do on a charge. Okay, no, there's electric field, okay, there's electric field potential and there's electric field potential energy. Electric field potential energy is the work done itself in moving that charge. So the work done by the charge in moving that charge from any point, that's why we use infinity, okay, from any point or infinity to a particular point, that's the electric field potential at that point. Work done per unit of charge, that's the electric potential. Work done per unit of charge. No, let me break it down. Let me break it down. Electric potential and electric potential energy. So let's separate between them. Electric field potential energy. Potential or electric potential energy. Electric potential energy. We call it electric field potential because that energy is within that field. Okay. Potential energy and just electric potential. Now, electric potential energy, since it's an energy, will be measured in joules. Is that okay? So, electric potential energy will be equal to work done. Is that okay? So, V will be equal to the work done and bring. Now, it's denoted by V. That's one thing. It's denoted by V. Electric potential is denoted by V. So, that's why when we do potential difference, you understand what that means. So, the work done is electric potential. And now let me explain what that is. If I have a point positive charge here, for example, and I have, you know that it has this field like this, outside, I'm going outward like this. If I have a point negative charge, now, what does this charge, what will this charge naturally do? This charge will naturally move into in this direction from point A. Let's bring it on a straight line so that we understand. So, because direction matters. So from a point A here to a point B here, do we need to do work in bringing this charge from point A to point B? Do we need to do work? No, because this thing will naturally want to move towards it because what? They are different, they are unlike charges, so they will attract. So because of this, if this charge A is moving in this direction, its potential energy or work done in bringing it will reduce. Does that make sense? That is work done on it. So you remember from thermodynamics, we said that if a system does work, if work is done on the system, total energy increases. But if the system does work, if work is done on this charge in bringing this in, number one is that no work is done on this charge. That's what you should know. Because this charge will naturally move here because it's attractive. And it's attractive. But if this charge were to be taken away from this field, from a point A to point C now, because the force on it is already attractive, then work needs to be done to bring it here. So because of that, the energy, the electric potential energy of this guy, energy now, or work done on this guy will increase. So when work is done on the system, that's what I wanted to tell you now. When work is done on the system, electric potential energy is increased. But when work is done by the system, electric potential energy reduces from thermodynamics. Work is done by the system, total energy what reduces. Work is done on the system, total energy increases. Don't forget that. So, but what if it was a point positive charge that was brought here, that was to be brought into here? If you bring this positive charge to this point B from point A, you have to do enough work on the system because these charges should repel. So there's a force pushing it away. So what you're trying to do is that you're moving against the force. So when work is done against the direction of force, direction of force is where? Here. So when work is done against the direction of force, then potential energy is positive. But when work is done against the direction of, when work is done in the direction of force, if it was brought in this direction, then this guy, electric potential energy will what? Reduce. Will reduce. Electric potential energy will increase in this direction, A to B. Electric potential energy will decrease in direction of B to A to C. All right. So this guy here is what? Electric potential energy is what? Work done. Electric potential energy is work done. So we can say that, and we know that work done is equal to force times distance. Does that make sense? In this case, force times distance R. All right. So and recall that W is equal to F is equal to K QQ over R squared. So times R. Does that make sense? So electric potential energy is equal to R takes care of 1R, KQQ over R. This is the formula for electric potential energy. But electric potential itself, that is V, electric potential itself. So this one will represent it to W. Electric potential energy is W. Is that okay? Why this is electric potential? They are not equal, sorry. Electric potential is not equal to the electric potential energy. Electric potential energy is the work done itself. Electric potential is the work done on a unit charge. That is work done on, so this is it now. Electric potential energy is the work done on this system to bring it to this point. But electric potential itself is the potential energy that per unit of this charge has at a particular point. Say for example, as it moves from point A to point B. So we call it the work done per unit of charge. Is that okay? The work done per unit of charge brought from infinity to a point. We read electric potential according to a point. So we say electric potential energy, electric potential at a point is the work done in bringing a unit charge from infinity to that point. So the work done per unit of that charge brought to that point. So we say that V will be equal to, what is W? W is KQQ over R, isn't it? So all of this over Q. So when you are dividing by a whole number, this guy will go under because you are dividing a fraction. So this fraction will come down. Then we have V equal to KQQ over R. You can go for that to say divided by Q over 1. So today the times 1 over Q. Q takes care of Q. So that V will be equal to KQ over R. Is that okay? So this is the formula for electric potential. So there are two differences between them. This one is the work done. Electric potential energy is the work done on that charge when you bring it from a point to a point. Why electric potential? And we also talk about potential difference. Well, we'll talk about it in the detail. But electric potential itself is the work done on a unit charge brought from infinity to that point. Not the work done on the system. The work that a unit charge of that charge, a unit of that charge rather, does in moving from any point to another. So that is what we have as electric potential. Then we said this one is energy. So it will be measured in what? In joules. This one will be measured in what? Electric potential is measured in volts. It's measured in what? In volts. Right? Or Coulomb. So what would that be? Let's get the unit. This is Newton. What is the unit of that? We have our K is Newton meter squared per Coulomb squared times Coulomb over meter. All right. So this takes care of this. This takes care of this. So we have Newton meter per Coulomb. So this is electric potential or volts. Is that okay? Good. It is named after Alessandro Volta. All right. Now, so what would be the electrical potential difference? So between 2 points, electrical potential difference will just be the you know that this, so it will just be electric potential difference will be equal to electric potential at a point A minus electric potential at a point B. Is that okay? So that will be the electrical potential. So, and you can even begin to generate equations from here. If the potential difference changes in those 2 points, if 2 points have different potential energies, it means that our work done on that moving in that. So if I have a point positive and a point negative charge, the work done in moving from here to here, moving from these 2 points, from a point A to point B, moving anything, maybe any charge rather now, from that point A to point B, will be giving us V times Q, that is QV, right? So because the potential is not equal at both points, then work done will become Q times change in V. Does that make sense? All right. So now let's now go to, now what's now the relationship between electric field intensity and electric field potential? So remember that electric field intensity we said was E equal to KQ over R squared, I think. KQ over R squared, yes. So here, K will be what? K will be equal to E R squared over K, right? And we said that V was KQ over R. So it means that K also will be equal to VR over Q. VR over Q. So let's bring them together. So if the charges were the same now, if the charges were the same, what would we have? We'd have that since K is equal to K, then we equate both. So let's call this equation 1, equation 2. Equation 1 equal to 2. Then we have ER squared over Q is equal to VR over Q. So Q can take care of Q. Is that okay? R1R will take care of 1R, then we have V equal to ER. Is another formula. But in some textbooks you might see VD there. But since we have been using R convention for our distance, then this is another formula. But these are the formulas you have for electric field potential. V is ER, or V is work done per Coulomb. Alright, so if the work done is given to you, you can easily solve with any of these formulas given on the board. Now, let's go to the last part of this, which is very important, and that is capacitors and capacitance. Capacitors and capacitance. Now, what are capacitors? A capacitor is a device that is used to store electric charge. A capacitor consists of two parallel plates. So, two parallel plates. We call this kind of capacitors parallel plate capacitors, of course. So you see that there's a space between these two plates. These are parallel plates. These are parallel plates. Now this one, so they are connected. So this is my circuit, for example. This is my circuit. So these two plates are connected together. So this is my capacitor. Is that okay? That is why we represent it with this symbol in electricity. This one, don't confuse with that of battery. Battery, there are two potential different. There are 2 points that have different potentials. So that's why we have this. So, but this, it stores charges. Besides the device that stores charges, right? It stores charges in form of electric field. It stores charge in form of electric field. So one point will be positive charge, feel the positive charges. The other point will be field negative charges. Is that okay? All right. So it works like it's not a battery, but it works like a battery. The principle of storage here is like that of a battery. All right. Now watch what happens. How do we now the space between them first? Let's talk about the properties it has. The space between them is called is an insulator in between them, or a dielectric. So we have, if our circuit was like this, we have two parallel plates. Plate 1 and plate 2. So in between them, we have a dielectric. That is another name for the insulator. It could be wax, it could be air, it could be, so there are many things. Mica, is that okay? That are used. Okay, so I mentioned air, I mentioned mica, all right? It could be wax also. That's this space here. That does not conduct electricity basically. But this will be positive, this will be negative. So now this is the point. It stores electric charge. Is that okay? Now, there is something about it. The ability of the capacitor to store electric charges is called its capacitance. Before we measure capacitance, there are some things about this guy that you must know. Okay, I've mentioned that. Now, so what is capacitance? Capacitance is the ability of the capacitor to store charges. Capacitance is the ability of the electric field to store of the capacitor to store electric charges. So the capacitance is given by the quantity of charge. The capacitance first is represented by C. Is that okay? Is represented by C. Is that okay? So it's given by the charge per unit of the quantity of the capacitance is charge stored no. So we said it's given by the charge per unit of electricity, by units of electricity voltage supplied to that guy. So it means that the quantity of charge stored by a capacitor is given by the capacitance of that capacitor times the voltage of electricity that is passed through it. All right. So that is the formula of capacitance. These are the formulas you should know about capacitance. And there's something about the capacitance. Now, the capacitance of the capacitor is dependent on two things. One is directly proportional to the area of the surface area of the plates, of the two plates. So if the surface area is great, then the capacitance of the capacitor will be able to store more charges. That is, the capacitance is high. And it's also dependent on the diameter of the charges. I said diameter. The distance rather. The distance of the charges. The distance between the charges. Of the distance between the plates. So it's inversely proportional to the distance between the plates. Is that okay? So the farther away the plates are, the lower the capacitance of the guy. So we have our constant here is our permittivity of free space. So we say C is equal to permittivity of free space, epsilon naught also, A over D. This is one other formula you should know, equation 3. There's one other formula with this, because there are different materials have their relative permittivity. So have their permittivity. So we say relative permittivity, therefore, which is the permittivity. When you say something is relative, just compare the relative of that thing, the permittivity of that thing to a standard permittivity. So we have that it is permittivity of that medium or material over permittivity of free space. Permittivity of free space is epsilon naught. So relative permittivity is this guy. So permittivity of a medium is the relative permittivity times permittivity of free space. And what I'm saying is epsilon naught is permittivity of free space. Is that okay? Or vacuum? So permittivity of free space. So the last thing that I want to talk about is energy stored in a capacitor. Energy stored in a capacitor. Now, what is the energy stored in the capacitor? The energy stored in the capacitor is given by the following formula. It's given by, you recall that the charge is CV, right? The charge stored by the capacitor is this. So the energy stored, I think it's gotten by integrating these functions. If you integrate it, what you're going to have is the energy stored is going to be the half CV squared. I'm quite sure that it's the integration of this guy, but you don't need to know that. Just know that E is equal to half C squared. So when you have that E is equal to half C squared, recall that C from there, C was what? Q over V. So we now have the half C is Q over V dot Q over V dot V squared. This cancels out and we have that E is also equal to what? Half QV. Does that make sense? Then V from here also, V is equal to, what will V be here? V will be equal to Q over C, right? So we can also plug that in, that E. So this is our equation 1 here, equation 2 for energy stored, energy stored. Okay, so E will be equal to 1 over 2 Q dot Q over C. Is that okay? Q times Q squared. So E is equal to 1 over 2 Q squared over C, or Q squared over 2C. That is equation 3. So these are all the equations that we need to solve questions. Now, capacitors might be arranged in two ways in a circuit. Capacitors could be arranged in two ways in a circuit. Now, one of the ways in which it could be arranged is the parallel arrangement, and the second is the series arrangement. I'm going to show us how that is done. So capacitors can be arranged in two ways. Arrangement of capacitors. So if you arrange capacitors in series, what do you have? The first method is the series arrangement. Series arrangement. If you arrange capacitors in series, this is how we arrange in series, like this, like this, like this, like this. So this will be capacitance 1, capacitance 2, capacitor 1 with capacitance 1, capacitor 2 with capacitance 2, capacitance 3, capacitance 4, like that, like that, like that. Is that okay? So the equivalent capacitance here, or the total capacitance here, will be equal to 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 plus dot 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 dot. It continues on and on like that. But what if we had capacitors in parallel? Capacitors arranged in parallel. Now capacitance in parallel is going to be something like this. Recall, I have taught us in resolution of circuits that when they are separated by a junction, if they are bounded by a junction, it means that they are in series. But if they are separated by junctions, then they're in parallel. So this is a parallel arrangement. If this was C1, C2, and C3, then equivalent capacitance here is equal to C1 plus C2 plus C3. So what that means is that in order to get the maximum capacitance in a circuit, this is how you must arrange your capacitance. To get more capacitance or more charge stored, you arrange your capacitors in what? Parallel. Don't forget that. Then series arrangement of capacitance reduces the what? Capacitance of the circuit. All right, now let's go on to solving a few questions before we call it a day. Okay, let's solve this 4 JAMB questions. I promise you I'm going to be releasing more and more questions. So when I'll be doing my 7-day series on JAMB physics and JAMB chemistry, I'm going to be revealing more questions in this aspect. But the video is already long, so I just want to make you make do with this. All right, so let's do this. We have this guy, this circuit arrangement, and we're told to find the equivalent capacitance. So this one is very simple. What you have is this. So you have number 1, so we have solution. Now, number 1, these guys are arranged like this. You have the 2 microfarad. Okay. Now, one thing I didn't review was that capacitance is measured in farad, right? It's named after the physicist Michael Faraday. Is that okay? Michael Faraday. So it's farad. Just like we have millifarad. M farad means millifarad. That is times 10 to the power minus 3 farad. Is that okay? Microfarad times 10 to the power minus 6 farad. Picofarad times 10 to the power minus 12 farad. Nano times 10 to the power minus 9. All right. So just as it applies. In this case, we have microfarads. So you have this connected to 3 microfarads. Then you now have this 2 microfarad here, 4 microfarad here, and then we now have 4 microfarads at the end. So what you see is that this guy and this guy are in series, but this guy and this guy are in parallel. So what do? We resolve the parallels first. So let's resolve the parallels first. Let's call this one C1, C2. So C will be equal to C1 plus C2 in parallel. You add them up like that. C is equal to 2 microfarad plus 4 microfarad. That gives us what? 6 microfarad. Is that okay? Very simply. So what we now have is what? The arrangement has become like this. 3 microfarad, then we have 6 microfarad. The equivalent capacitance is 6 microfarad and 4 microfarad. So here now we now have series arrangement. So what do we do in series arrangement? 1 over C is equal to 1 over 2 microfarad plus 1 over 3 microfarad plus 1 over 6 microfarad plus 1 over 4 microfarad. The LCM of 12, right? 2 in 12 is 6. 6 by 1, 6 plus 3 in this 4 plus 2 plus 3. I'll be understand what I'm doing. So 1 over C is equal to that. So 1 over C will therefore be equal to 10, 15 over 12. 3 goes here 4 times, 3 goes here 5 times. So we have 1 over C will be equal to 5 over 4. So that C will be equal to, invert it, that becomes 4 over 5, which is 0.8. 0.8 microfarad or 0.8 times 10 to the power minus 6 farad. And that is all here. Or 8 times 10 to the power minus 7 farad. So you can see this in the option. 8 times 10 to the power minus 7 farad. That's the answer. Alright. Number 2 says a capacitor, this. So the capacitance of the capacitor we are given is 8 millifarad. Millifarad. Take note of that. Millifarad. Millifarad will become what? Will be equal to 8 times 10 to the power minus 3 farad. It's charged to a potential difference of that. So the charge or the voltage or the potential difference that is acquired, across the two plates, the potential difference is what? It's called is what? 100 volts. 100 volts. It now says the energy stored in the capacitor. So remember our formula when we have CV, E energy stored equals to what? Half CV squared. This equals 1 over 2 times C, which is 8 times 10 to the power minus 3 times V squared, 100 times 100. Is that okay? This takes care of this. We have 4 here. Equal to 4 times 10 to the power minus 3 times 10 raised to the power here, 10 to the power 4. Does that make sense? So we have 4 times 10 to the power 4 minus 3, that is 4 times 10, which is 40. Is that okay? 40. Now, energy stored, 40 what? Joules. Alright. The next one, a parallel plate capacitor of area that. So we have area A, this is number 3, number 2. Number 3 says area is 10 centimeters squared. Now, immediately convert it to meters. It's very simple, just follow me. You know that, how many centimeters make a meter? 100 centimeters is equal to what? 100 centimeters will give you 1 meter, right? Look at this space I left here. This one I left this space because what gives us centimeter square is centimeter times centimeter, right? So we can say centimeter times centimeters gives us what? Meter squared, right? Right? As in centimeter times centimeter means meter times meter. Does that make sense? This is centimeter squared, isn't it? Okay, yes, this is how to begin it. Watch what I want to do. I want you to declare to you the conversion. I just want to impute a number, then you say that, how did I get it? So what we have here is centimeter squared, right? And what we have here is meter squared, right? This thing means centimeter times centimeter. Does that make sense? So this one means meter times meter. How many centimeter will give us 1 meter here? It is 100 centimeters times 100 centimeter. 100 centimeter is what? 1 meter. 100 times 100 centimeter is what? 1 meter. So what does it give us? 100, that's 10,000 centimeters is equal to what? 1 times 1 meter squared. Does that make sense? Good. So if this is the case, 10,000 centimeters squared is equal to 1 meter squared, then 10 centimeters squared will be what? X. So you can cross multiply. So that X will just mean that you are dividing this guy by 10,000. So next time, When you are converting from centimeter squared to meter squared, what do? You divide by 10,000. So you know I got it now. So equal to 10 over 10,000. 1, 2, 3, 4. 1, 2, 3, 4. So what we have is x is equal to 0.001. 0.001 meter squared. So that's our area. 0.001 meter squared. All right. So the question after that says that in a vacuum, has the capacitance of that? The capacitance is 10 raised to the power minus 2 millifarad. 10 raised to the power minus 2 millifarad means 10 raised to the power minus 2 times 10 raised to the power minus 3 farad. Don't confuse it. Don't say 10, 10. It is not no, it shouldn't confuse you. This times 10 raised to the power minus 2 millifarad. What is the distance between the plates? So we are looking for distance or R between the plates. And recall that we are given epsilon naught is 9 times 10 to the power minus 12 there. Then recall the formula that we said that capacitance is directly proportional to the area, inverse proportional to the distance, given that the permittivity of free space is constant. So that we have that our distance will now be equal to, just interchange them here, interchange them. So E D will be equal to what? Epsilon naught times area of our capacitance. So that will be 9 times 10 to the power minus 12 times area, which is 0.001 all over. What's the capacitance? 10 raised to the power minus 2 times 10 raised to the power minus 3. Does that make sense? So very easily, you see that this thing, 10 raised to the power minus 3, is the same as this guy. This is 1 times 10 raised to the power minus 3, right? So this can take care of this like that. You see that? So what we have is 9 times 10 raised to the power minus 12 times 10 raised to the power, now, here divided rather, by 10 raised to the power minus 2. So I want to change the plus. So we have 9 times 10 raised to the power minus 12 minus 2. That is what? Plus 2. So this is what? Minus 10. So the distance between them, D, is equal to 9 times 10 raised to the power minus 10 meters. So of course, that's the answer in meters. All right. Now the next one, which is the last, number 4, says that calculate the force acting on an electron. Calculate the force, number 4. Calculate the force acting on an electron. Now this one is an electric field, I think. On an electron, charge of electron is what? 1.6 here. We know that 1.67 times 10 to the power minus 19 Coulomb. I've mentioned this in the previous video. Placed in an electric field intensity that. So E is 10 raised to the power 8 volts per hand. Now, volts per meter, this should not confuse you. Because you recall that we generated this formula V equal to ER. So what this means is that E can also be what? Volts per distance, right? So volts per distance, that is the potential, electric potential per distance between them, is also the electric field intensity. That's where this unit is coming from. Because remember that, so it means that this unit, volts per meter, is equal to, you know, E is F per Coulomb, right? That is Newton per Coulomb, right? F per charge. So that will be, this is equal to Newton per Coulomb. That's just the case. Is that okay? And of course, you can generate any other formula from there if you want. So from here, we can just say that we are giving the voltage, the E, we have been given E, and we have been given the charge. Yes, we are looking for force, right? So we can relate them. Since we know that this V over R is equal to F over Q. Now, our formula connects E and Q. Oh, we are using this. Is that okay? That is E. E is V over R, which is this. So E, so F will now be equal to what? EQ. Just multiply them. Very simple. So, very simple rather. So we have E equal to 10 raised to the power 8 times 1.6 times 10 raised to the power minus 19. So what we have is what? Minus 19. 8 minus 19 is what? Minus 11. So that we have F to be equal to 1.6 times 10 raised to the power minus 11 Newton. That will be it for this video. If you did stick to the end of this video, I pray that God bless you and will help you to pass all your exams well. Do well to share them now. Don't stop at staying to the end. Share the video. Share the video with your friends and colleagues, and God will increase you. Amen. God bless you. Make sure you are subscribed to the channel also.